So a very good evening, guys. So in this particular session, we are going to discuss about the week 4 content. Okay. So the lecture of the week 4 has already been over, and you have you might have seen those videos of the Rajesh Prasad. Okay. So in this particular session, let me share my screen. Okay. Yeah. So in this particular session, we are going to discuss about the week 4 content. That we will solve numericals based on that, and we'll discuss whatever doubts you are having. You can see these recorded videos on the YouTube, and you can comment on those if you have any doubt based on that, and I will definitely respond to it. Okay, so let's get started. I will switch off my video so that we have a better quality. Yeah, so let's get started. This is talking about the week 4 content of the Crystal Symmetry and Tensor course. The list of the topic. So the list of the topic that has been covered in this particular weeks are the stereographic projections, the definitions of the symmetry, what is a group, we have studied about those things, and the matrix which is representing the symmetry operations. And we see the few properties of the this matrix which is representing symmetry operation, symmetry matrix, and that is a W. What its trace information will give us, and then we have also studied about how the coordinate transformations and symmetry operations are related if we want to change the basis of our study. Okay, so this was all the thing that has been covered in the week 4. I've seen the assignment questions, so most of them are based on the stereographic projections and the coordinate transformations, the symmetry operations and all. We'll also try to focus on those things. Okay, so let's start with the first question, question number 1. So the question number 1 is regarding the stereographic projections. So it is asking that stereographic projections, the options are there, we have to select the correct statement. The stereographic projection is a area 2 projection. The first of the option is it area 2 projections? Focus over here. Second option is telling that stereographic projection is a angle 2 projections. Okay, and then we have the third options, which is talking about the orthographic projection. It is whether it's the area 2 projection or the area angle 2 projection or the area 2 projection. See, in stereograph, we know that if I am drawing one of the stereograph, I know the points which are located over here. Let us say on the projection plane, if it is located at the circumference, we know that this point is representing the direction, and that direction is at the 90-degree from the center. So it is representing some particular angle. So the distance in the stereograph projections are represented the angle. So this is the angle has been preserved. The symmetry has been preserved over here. Okay. So in that manner, we can say that the stereograph stereographic projection is a angle 2 projection. So option B is the correct option. Orthographic projection is not the angle 2 projection, and you can also see, but just by the basic visualization that the orthographic projection is will not also be the area 2 projection. In some case it can be, in some case it cannot. Okay, so in that manner we can say that we have finished our question number one, and the only thing that we need to understand from this question is that the stereograph will preserve our symmetry since it is preserving the angles. And so uh, most of the crystallographers, what they do is they take the diffraction pattern. If they don't know the what the symmetry the particular material is holding, they will take the diffraction pattern, and based on the diffraction pattern, the pattern which they have observed, based on the symmetry of that particular pattern, they will go to the they will understand that which symmetry the particular stereogram which is they are getting, which symmetry is holding for that. So we can say that the stereograph is an angle to projection. It will preserve our symmetry, and that was the question number one. Let's move ahead and go to the question number two. The question number two, there are the multiple parts in it that which of the following at the is slash are the correct. It means that multiple can be the correct options. The question number one, sorry, let's focus on the option A. We will not see the remaining options for a time being. We'll just focus on the option A, that what it is telling at. Vertical plane is projected as a great circle of an infinite radius in the stereographic projection. In the video, in the lecture which is done by the Professor Rajesh Prasad, we have seen that the how we can project the stereograph. So the points, sorry, the direction will be presented as a point. Or we can say that it will be presented as a pole. While the planes will be presented as a line, or to be more precise, it will be presented as a, it will be projected as a great circle. Line is just a special case of circle having the infinite radius. Right. So line is just a special case of a circle which is having the infinite radius. So here we can say that how we know that the vertical planes are going to be projected as a line. If you draw the stereograph, if you project a particular vertical line, sorry, vertical plane to it, it will be projected as a straight lines. There are multiple straight line depending upon the orientation of the particular plane. So a plane can be like it can be straight over here, and then it can be like this. But all of them are vertical only. So all of them will project as a line. But the thing is that we can call them as a circle, and it will be the great circle, but their radius will be infinite. And so we can say that yeah, vertical planes is projected as a great circle. Yeah, they will be projected as a great circle of the infinite radius in the stereographic projection. So we are talking about the stereographic projection. So option A is a correct option. What about the option B? Let's see that. So the directions are projected as line in stereographic projections. So So the option B is telling that the direction. It's talking about the direction. Okay, it's talking about the direction, and it's telling that the direction is projected as a line in the stereographic projection. No, it is not the case. So it's not the case. Directions will be presented as a point. It will be presented as a pole. So the dimensions of the direction, if we note down the dimension of them, let's do it over here. So for the direction, it is having the 1D. In the stereograph, it will be presented as a point, which is 0 dimension. So the dimensionality has reduced by 1. While we talk about the plane, in the real space, it is represented as it is a 2D. But in the stereograph, it will be represented by the line or a curve, which is a 1D. So whatever we are presenting in the stereograph, the dimensionality of it getting reduced by 1. So we can say that the directions will only be presented as a point, and our second options, which was telling that the direction are presented as a line, will be the incorrect one. Let's go to the third option now. Third option is telling that the points lying on the circumference of the primitive circle are perpendicular to the horizontal plane. So it's talking about the horizontal plane. We'll draw the horizontal plane in the primitive circle, and then we'll take a point on the circumference of the primitive circle, and we'll see whether what are the relation between them. Like what is the angular relation between them. Okay, so let's take this page. So let us say I'm drawing one stereograph. So this is a primitive circle. The one which I am drawing is a primitive circle. This will be the vertical direction, which is represented as at the center. It will be the vertical direction. At the circumferences over here, all these places, they will be the projections of the stereographic projections of the horizontal directions. So they are the horizontal direction. While the horizontal plane itself will be the primitive circle. So this entire primitive circle, if I am drawing, which is this entire thing, this will be along with the primitive circle, it will be the horizontal plane also. So this is our plane, and this is the horizontal direction. The horizontal direction and the horizontal plane are lying onto each other. The direction is lying onto the plane. So the angle between the plane and the directions. Note that it is not talking about the angle of the plane normal. It is talking about what is the angle between the plane and particular horizontal direction. So since the direction is lying onto the plane, the angle is 0. So it is not the perpendicular. So the directions and the plane, they are not perpendicular to each other. Instead, they are aligning. They are on to each other. So we can say that the point lying on the circumference of the primitive circle are perpendicular? No, it is not perpendicular. And that's why the option C is incorrect. Now, we uh, did with our first three parts. The last one is stating that the radius of the primitive circle is half the radius of the reference sphere. So it is talking about the relation between the radius of the primitive circle, it will be rotated by Rp, and the radius of the reference sphere, that is Rs. It's very easy. Let's understand that by drawing the stereograph. So let us say this is our reference sphere. And the way we have constructed the things, let's say this will be our, the projection, it will be the primitive circle. Which is the intersection of the projection plane with the reference sphere. So what is the radius of this particular primitive circle? The radius is this Rp, and the radius of the reference sphere is again Rs. From the geometry, we can say that from the geometry it is the way it is. Rp is equal to the Rs. And so the radius of the primitive and the radius of the reference both are exactly equal with each other. And that's why our option D is incorrect. Okay, so the only correct option which we are getting here is a vertical plane is projected as a great circle of an infinite radius in the stereographic projections. The second option, which was direction are projected as a line in the stereograph, it was incorrect. The point lying in the circumference of the primitive circle are perpendicular to the horizontal plane. No, it is not. It's not the case. It is incorrect. The radius of the primitive circle is half of the radius of the sphere, reference sphere. It is also incorrect. Okay. So with that, we have solved the question number 2. Now let's move to the question number 3. So with the help of the question number 1 and question number 2, and the assignment questions, which was based on the stereographic projections, it will be easy to solve. Now let's go to the next question, question number 3, where we need to discuss about the symmetry operations. We have to comment on the symmetry operation of the cubic crystal represented by the matrix. We know there is something called a symmetry transformation matrix, which is W, and they are the W. So this itself is a two question where we have to discuss first about the option A, then we have to discuss about the option B. So we need to comment on this particular symmetry transformation matrix. Comment means we need to know whether it is proper or improper. we need to know whether they are accomplished by the rotation, reflection, or inversion. And the last thing is that their combinations or their combination. So we need to know that this particular matrix, what it is representing. Okay. So how the basics which has been covered in the class, I will just revise that. Will take I will take on that so that we can easily solve these questions. So this is our symmetry transformation matrix, which we will get their columns we will get when we multiply them with the 100. We'll get the first column when we multiply this with the 100. So overall, whatever the results which we will get the first column of this particular transformation matrix. So effectively, what it is doing that this symmetry transformation matrix, its first column is telling that how I am going to transform this particular 100, 100. Second column is telling that how I am going to transform 010, and the third one is telling that how I am going to transform 001. So if one knows that the how their 100, 10, and 001, these three directions are going to be transformed using the symmetry transformation matrix, then we will be in the condition to comment on any of the vectors, how it is going to transform by the particular symmetry operation. Okay, so here also we can say that the first column is a how the 100 is transformed to the our new system, which is after the rotation or the particular symmetry operation is taking place. Okay, so now let's go to the this particular question number 1 of it. So the question number 1 is 100. So W is given 100 O minus 100 This is our W, and this is the first column. It is telling that how I have transformed the 100. We can see the initially it was initial and final both are same. So this particular direction, if I draw them, X, Y, and Z. So the X is remaining at its own place. It's not changing itself. So the initial is drawn with the blue color. Let me draw the final with the black color. So the finally is also it's at the same place. While second column is telling that how that O is transformed. And we have seen that it has negative. In the x direction it's not changed. Its y coordinate is not changed. Y component is not changed. But in the in z component is not changed, but in the y component has become just negative of it. So the y, the initially which was like this, it has transformed to over here. And the z also, it is remaining as it is. So the final z is also like this. So now we need to think that how we can change the y from positive, which operation can change y from positive to the negative without affecting z and without affecting x. Z and x are forming a plane, xz plane, and that plane is invariant right now. We can say that only y component is changing, the y is changing, and it can be done only by the reflection. So the plane, the mirror, if we place along this particular y and x, it will transform our y, sorry, z and x, it will transform our y to the negative of y, and it can be done by the reflection. Okay, one more thing, which kind of operation it is a proper or improper, that is kind 1 or 2. It can, we already know that reflection is a kind 1 operation, but still let's solve it, and using the determinant, we know the determinant of the W symmetry transformation matrix. If it is a plus 1, it is a proper. If it is minus 1, it is improper. Okay, so what? Let's try to find its determinant. Uh, it's very easy. One remaining two column will be 0 only, so we have to multiply 1 with the simple multiplication is there. 1 multiplied by minus 1 times 1 plus, sorry, minus of 0 times minus 1. So we will get over here 1 multiplied by minus of 1, and this will be 0. So effectively we are getting minus 1. So yeah, again we have proved that this particular reflection which we are getting is minus 1. It's an improper operation, symmetry operation. Okay, and that's how we have solved this particular option A. I hope it is clear, and if there is any doubt regarding this, you can put on the comment box. I will definitely respond to it. Okay, so now let's move to its second part. In first part, we have said that okay, it is reflection. We have commented on the symmetry operation which is occur, and also we commented whether it's a proper or improper. Now let's go to the option B. Second one, second question. 1 O minus 1 and O minus 1 O. Let me write it in the blank sheet. Next, this is the symmetry transformation matrix. Let's start with drawing our axis. X, Y, and Z. So this is the initial axis. Now, based on this particular symmetry transformation matrix, we'll comment that how our axis is going to change, and how our y is going to change, and how our z is going to change. So let's focus on the first column right now. So the first column is telling that how 1 is getting affected, and we can see from initial, which is 1 it has transformed to the 1 itself. So that is, it has remained at its own place. The operation, the symmetry operation is occur in such a way that it's leave the x to be the invariant. Now let's go to the second option. It is telling about how O1O is transformed. So if I draw this, which is transformed to the OO minus 1, how it will be? It will be in the negative of Z. That's how it is. So the Y has transformed to over here. Let me call it to be the Y dash. It will be X dash. Now let's talk about the this last one. How Z is transformed. Z has transformed to the O minus 1 O. That is, it in the negative of Y direction. So the this is how our Z is. Sorry, not Y. It will be Z. Instead of writing minus, I will write dash. Now we need to think how we can change our axis, like which operation, by what operation it can be done. X, Y, and Z. What we can do to make sure that X will remain at X, Y get to the minus of Y at the in the Z direction. This is X dash, Y dash, and this is Z. This is something which we need to do. So the what is left over in this particular thing is that which what is invariant is X. It has not changed. While remaining two axes are changed. So there is a slight intuition which we are getting that it might be rotation. Rotation along the x-axis. It might be possible. But we know the rotation is a first kind, proper transformation, right? It is not going to change the handedness. And so the determinant should be 1. If it is rotation, the determinant should be 1. Let's try to find the determinant of it. So what we are getting a determinant is that this 2 will be 0 itself. So 1 multiplied by this is 0 minus multiplication of this minus 1 times minus of 1. So we can see that it will be 1 into this, both will be plus, it will cancel out with each other and will be minus of 1 left. So we can say determinant is minus of 1. Pardon. And so determinant we can say that it is a minus of 1. Right. And so it cannot be the rotation itself alone. Since the handedness, the change in the handedness is involved over here. So for a time being, let us rotate about the x-axis and make this y and z in the rotation manner. So what we will get if we make them in the third quarter. Let us rotate by 180 degree about the x-axis. So y will get to this particular position. Call it that y double dash for a time being. Z will get to this particular position. We can call it to be the z double dash. Now consider this. Initially our x and y was like this. This was our x and this was our y. Sorry, y and z. This was our y and this is our z. After we rotate by 180 degree, we got y over here, y double dash, and z over here, z double dash. But this is not something which we wanted. What we want this y to be come over here and z to be come over here. This can be done if we place a mirror along this. This position will be changed. Their position will be changed. And then this will transform, its final shape will be transformed, that z will become over here and y will come over here, which is what we needed. So rotation about the reflection about the reflection at the angle of 45 degree, plane which is at the angle of 45 degree and along the x-axis. If I place a plane right over here, I will get the reflection. So the entirely what we have concluded over here is that in order to transform from our initial state x, y and z to the x dash, y dash and z dash, we need to do what we need to do, the couple of operation we need to do, couple of symmetry operation we need to do. First is the reflex, first is the rotation by 180 degree, and this rotation is along the x-axis. Its rotation, axis rotation is along the x. Then we need to do reflection, and the reflection plane we know that how it is in such a way that it is at the 45 degree to both the x and to both the y and z axis, and it is along the x-axis. The plane is covering the x-axis, and that's how and also we have determined that the its determinant is minus of 1, that is improper, and it is happening because of the reflection. Reflection is improper, rotation is a proper. It is not going to change handedness, but reflection is going to change handedness. So effectively, when I combine this, I will get the determinant of minus of 1, which is saying that yeah, the handedness are going to change. And that's how we have solved this particular question number B, which is a combination of rotation and reflection. And one just need to visualize, one just need to understand that how, which symmetry can do this particular type of changes to occur from the initial state to the final state. Always draw x, y and z axis first, and depending upon this particular symmetry operation, this symmetry transformation matrix, draw your final state, and then try to know that how you can achieve the from the initial state to the final state, how you can, what transformation can lead you to go from state 1 to state 2. And that's how we have solved this question number 3. So the both part of them are solved. Okay. So if you find any difficulty in this particular thing, uh, you can always comment on the videos, and or if possible you can also ask on the doubt forum, discussion forum. Okay. Okay, so now let's move to the next question, question number 4. Let's read it first. Write symmetry transformation matrix. So now this time we have to write W, symmetry transformation matrix, for a cubic system in the following cases. Okay, let's go with the case number 1 first. So we need to write a W. So in the cube we are talking about, okay, so and it is telling that rotation is by the 90 degree about the 100. This is, since it is in the square bracket, we can say yeah, it is a direction only. So let's draw a cube. My drawing is not that great, but I will try to do it. Considering our initial x to be along this, y and Z. Now let's draw this rotation axis. So we know the rotation axis is is about the 1 1 0. I think there is some typo over here. It is not the 1 1 0. It should be, instead of this it should be it can be 1, sorry, not, instead of 1 1 0, it is 1 0 0. Or better, let's make it to the 0 1 0. So the direction is along the y axis. So we can say that it will be along this particular. So about this we are rotating by 90 degrees. So we are rotating by 90 degrees. Okay. Since it is not given to like in what sense it is rotating, clockwise or anti-clockwise, we can consider any of the case and we can discuss them. If it is mentioned in the question, then we can go with the particular case which is given. So now let us say I am rotating it like in this particular manner. That axis tending to the going upwards. So since it is about the y-axis, since it is about the rotation is about the y-axis is the rotation axis, that will be the invariant. Y is not going to change. So seeing from the y direction, let's plot our x. This is x and this is y. Sorry, this is z. We are seeing from this particular direction. Seeing from here, we can say this is our x and this is y, our z, and this will be the y-axis. Now we are transforming about this particular axis by 90 degree in this particular direction. So considering black one to be our initial, we can draw our x will be along, x will get to the, this particular final position will be the x dash. Y will get to the, this particular position, that is a, sorry, z will get to this particular position, that is z dash. And y dash, both will be at the same position. It's not going to change because it is invariant. We need to write the symmetry transformation matrix, which is having 3 columns. First column is telling that how x is transforming. Second is telling that how y is transforming. And third one is telling that how z is transforming. So we know that we can see that x is transforming to the plus of z. So in the x direction there will be the, finally we can say that there will be 0, 0 and 1. While y is not transformed, so initial position of the y was 0 1 0, 0 1 0, right? So it will remain as it is. It is invariant 0 1 0. What about z? Z is transforming to the z dash, which is in the opposite direction of the x. So we can write over here that it will be the minus of 1 O, and that's how we can see that this is our symmetry transformation matrix. So just knowing how our initial axis is going to transform to the final axis using the particular operation which are given, we can write our symmetry transformation matrix. And that's how we have solved the question number 1. Now let's move to the second part of it, which is telling that the rotation by 120 degree about 111. Okay, again we will draw the cube. We need to discuss about the rotation. By 120 degree about 111. Sorry, it shouldn't be in the this particular type of bracket, it should be in the box since it is a direction. Let's draw a cube. Our axis will be rotation axis is 111, that is considering this to be the origin, considering this to be the x-axis, this is y, and this is z. We have to move one along the x, one along the y, and one along the z, and we will get to the final position of this particular 111 direction. We can join them, we can join it, and we can say that this is our how we are rotating it. Again, let us say we are rotating in this particular manner. Okay, so this is our rotation axis 111, and we have to rotate by 120 degree. Let's try to see from this particular angle how my cube will look like. If I see from here, I can say it will be like this. I am drawing this particular things. For a timing, let us ignore that this is not, there is nothing is there over here. We can draw this particular axis how they are going to look like. So this is our z will look like this. X will look like something like this, and this will be the y. And this is a rotation axis which is 111. If we just project it, we are going to see something like this along the 111, and the angle between them, just by the symmetry, it is angle between them is 120 degree. Let us say my sense of rotation of about this particular 111 axis is along this. So we can say it will be 120 degree in the clockwise direction. One can consider the anti-clockwise also. So in both cases, nothing much going to change. The pattern, the way that we are dealing with the question is going to remain as it is. So this is what we have drawn the initial. How initially without the transformation, our axis and the x-axis and the rotation axis is going to look like. Now let's apply the transformation to it, and let me draw it with the blue color. Rotating about the 111, the x-axis about the 111 by the 120 degree, x-axis will get at to the position of z. So let us say this is our x dash, which is along the z. Z will get along the y. So let me call it to be the z dash, which is along the y, and this will be, and the y will get to the x position. Y will get to the x position. Let's call it to be the y dash. We know initially this was x. Initially this was z, and this one was y. So our 110, that is x, has transformed to the z, that is a 001. So if I will write a W, symmetry transformation matrix, x-axis we can say it is transformed to the z, x dash the final is along the z. So we can say that it will be 001. Y has transformed to the y dash, which is along the x. Y has transformed to the y dash, which is along the x, and we can say it will be the 100. And z has transformed to the y, and which is along the transform to the y, that is z dash is along the y, we can say that it will be the 0 1 0. And that's how we have found the symmetry transformation matrix if we rotate by 120 degree in the cubic system about the 111, this particular axis. And with that we have solved our question number B. Okay, so now let's move to the third question, option C, that is a sub part of the question number 4, the reflection. Again we have to write the symmetry transformation matrix only. The reflection in a plane passing through the x-axis and inclined at an angle of 45 about the x and y-axis. Okay, we have to do that. The reflection plane passing through the x-axis and inclined at an angle of 45 degree to the x and y-axis. It should be the typo, it should be the z and y-axis. Okay, so now let's try to solve it. The reflection in a plane passing through the x-axis. So again we are talking about the cubic system itself. So let me draw the three axes, x, y, and z. What we need to do? A reflection in a plane passing through the x-axis. So the x-axis is consuming this plane. The plane is within the x-axis is within the plane, and that plane is in such a way that it is inclined to the at the angle of 45 degree to the y and z axis. So let me draw it like this. This is our y and this is our z. Instead of trying in the three-dimensional way, let's draw in the 2D way, and we can say this is a x, this is a x, and our plane is inclined at the angle of 45 degree with the x and z axis. So it can be this plane, or it can be this plane also. So we have the two planes, 1 and 2, which both of them are inclined at an angle of 45 degree. And we need to write for this thing how our W, symmetry transformation matrix, is going to be changed, is going to look like. So the initial axis, we need to draw the initial and we need to draw the final. So initial is like this. Let's talk about the plane 1, how it's going to change. The plane 1, if we talk about the plane 1, so the x-axis will remain at its own place because the reflection plane is containing this particular x-axis. So it will remain as it is on place. So this is x dash. While the z and y is going to change their position, so z will come to at the y position. So it will be the z dash. We can call it to be the call it as, and this will be the y dash. And so the manner in which we have solved the first two parts, we can solve this also. The symmetry transformation matrix for the plane 1, we can say that the x has not changed. That x dash and the x both are at the same position. So we will write 1. Oh, oh. How y is going to change? Y has changed to the y dash, which is along the z axis. So it will be O, O, 1. And z has transformed to the z dash, which is along the y axis. So it will be 0, O, 1, O. And this is the plane 1 for the plane 1 we have drawn. And that's how the symmetry transformation matrix will look like when we do the reflection. Let's confirm that it is improper. Let's confirm it. So these two we are going to give me 0 anyway, so I don't need to write. While writing the determinant of the W1, we can say that the 1, there is a lag, it's fine. Yeah. 1 multiplied by, this will be 0 minus of 1 times 1. So effectively it will be minus 1 when we solve it. So yeah, it is an improper transformation, which is just giving weightage to our answer that yeah, the reflection, we found the reflection, and due to the reflection we are getting this particular transformation symmetry transformation matrix. And since it is representing the symmetry transformation matrix for the reflection, no matter in what the case it is, whether it's along the reflection is along the x-axis or y-axis or z-axis, considering which of the plane, whatever the plane, x, z plane, y, z plane, it will be the determinant will be minus 1 only. And that's what we are getting. Now let's go for the plane 2. So again, this particular x is not going to change if we talk about the plane 2. X will remain at its own place. So this is the x-axis. While if we reflect along this, we can say that the z is going to reflect it somewhere over here. So we can say this will be the z-axis. While y will be reflected over here, so it will be along this. This will be the y-axis. Let me do this in the next page. Considering this that it is already been done, so our initial was like this, x, y, and z. Finally, after the transformation, symmetry transformation, it is looking like x dash. It's along this. This is a y dash, and along this is z. one need to confirm. One is whether the particular set is forming the closure. B, whether they are associative. C, they should have the identity. For like we are talking about the for all the elements of the particular set. And D, they should be inverse of inverse should be available to us. Okay. So we'll start with the closure. See, associative in the all the symmetry operation, you will find that it will be associative. But uh, once we found the closure, now will in the process we will know that whether something is identity is available or not, or whether inverse is available or not to us. Okay. So in order to know the closure, whether the or particular elements that is uh, one one fold, two, four-fold, four. And this is a four-fold inverse. That is a it is a four-fold itself, but the direction is inverse. If it is someone if four-fold is in the clockwise, four inverse will be in the anti-clockwise 90 degrees rotation. Okay, so over here, so we can say that if I apply the anti-clockwise, so it will be along this. X will transform to the y. While if I apply the 90 degree, it is a four inverse. Inverse is telling that it is the opposite to the anti-clockwise. It is a clockwise direction, and this will transform to over here. And that's what we can say that the four inverse is there. Mx, that is the mirror along the x, that is talking about this particular mirror. My, my is a vertical mirror, and then m plus is a diagonal mirror, m minus is again a diagonal mirror. Okay, so we need to make a table, group multiplication table, and based on that, we can see whether they are forming a closure or not. Let's take a fresh page. So we are having the 1, 2, 4, 4 inverse, mx, m plus, my, m minus. Now we can just write same thing in the column manner. Okay, so now the operation which we are doing in this particular symmetry operations is a followed by. We have seen in the case of the how the professor has did for the h. We will do similar thing for the our square itself. So let's mark all the things, all the symmetries in the square for a time being, so that we know how things are going to change. So this is our rotation axis, fourfold. So one can rotate the fourfold, let us say fourfold, one times. Consider two dimension only. x and y. We are rotating by the fourfold, x will get to the y position. If I apply fourfold 2 times, what will happen? X will get to the negative of x direct. Let it will come over here and y will come over here. So instead of fourfold 2 times, we can say it is nothing but it is a twofold itself. So fourfold 1 times is we will write a fourfold, but fourfold 2 times it will be the nothing but a twofold itself. If I am applying 2 times fourfold, it will be the twofold itself. If I apply 3 times fourfold, what will happen? That this x will transform to this particular position, or in the other way one can say that x will transform to this particular position. The direction is, we can say that it's reverse. The way of getting the from final to the initial, from the initial to the final, it can be two way, either going from all the way over here or one can go from here. Then nothing is going to change effectively. So we can say that the 4 inverse, so applying fourfold 3 times, applying fourfold 3 times is nothing but the fourfold inverse. This is a twofold and this is a fourfold. So we can mark that this is our fourfold for a time being, and this we can say this is a horizontal mirror, this is a vertical mirror my, and this is the m plus diagonal mirror, and this is another diagonal mirror which is m minus. So now based on these things, we need to verify our property of closure. I made a mistake. Okay, yes, take the call. There should be the one also, and there should be the one also over here. Okay, so one, that is a one fold, which is followed by one fold, that is, which is not, it's not changing anything. It is also not changing anything. So effectively, it will be the one itself. One followed by two fold, like we are doing one fold, which is we are doing nothing over. Effectively, we are doing nothing. That is one fold is nothing. So, and then we are following by the two fold. So effectively, we are doing the two fold only. One fold followed by the fourfold, it will be the fourfold itself. One fold followed by the fourfold inverse, it will be the fourfold inverse. So all this first column, sorry, first row will remain as it is. Now let's go with the twofold. We are doing twofold, which is followed by the one fold. One fold is nothing, so it's not doing nothing means one fold. So we can say it is a twofold only. What about the twofold followed by twofold? How it is going to change? So let's get back to our this particular image. Consider a particular point. Let us say this is our particular point. Point 1. Apply twofold to this particular point about this particular axis. About this axis, we are applying the twofold. It will come from this particular point. Let me write 2, 3. 1 will get to point 3. So this is what we will get after one particular twofold. Now again it is followed by the twofold itself. So again this will undergo the twofold. It will come back again to the 1. So someone who not saw the process what is happening, they will say that nothing has happened. It was at this particular place, and again after the operation which is for twofold, and followed by twofold is represented as 1 itself. Nothing is happened. So we can say that the twofold followed by twofold is. Now write about the twofold followed by the fourfold. Okay, so let's take another page. Let us say this is representing the x and y axis of the square. Apply the twofold to it. So applying the twofold, let's make a complete square itself. 1, 2, 3, 4 across this particular thing, across this particular axis. If I apply the twofold, this x will transform to the 3. This 1.1 will get to the point 3 after twofold. After 9, twofold followed by the fourfold. So twofold is done. Now we have to do the fourfold on this particular point which we have obtained. If I do fourfold on this, it will get to the point number 4. Is there any other alternative by which we can go from 1 to 4 directly? Yes, there is. That is, instead of rotating like this, rotating like the clockwise manner, anti-clockwise manner, twofold followed by the fourfold, one can rotate in the anti-clockwise manner and it will be the fourfold inverse. Yes. So that's all. Twofold and fourfold is giving the fourfold inverse, which is itself is the one of the element. Now twofold followed by the fourfold inverse. Now we have to go with the next one. That is a twofold. We are doing the twofold and then the fourfold inverse. That is the in the clockwise manner we are doing the fourfold. Let's do it. 1, 2, 3, 4. These are the 4 points which we will focus on. This is the rotation axis. Rotate 1 by the twofold, it will get to the point 3. Now, from this particular point where we have rotated the twofold in the anti-clockwise manner, fourfold inverse, that is a rotate this particular point in the clockwise manner. So we will get from 3, we will get back to the 2. So effectively, we are changing from 1 to 2 itself. And this can be done by the fourfold directly. So we can say that yeah, it is also forming the closure. That is a twofold followed by the fourfold inverse is forming the closure and it is giving the fourfold. So we can write here to be the fourfold. In the similar manner, we can complete this entire procedure. Okay. So let's do it. If I do, let's go with another one. Twofold followed by the mirror, which is along the x-axis. See, twofold is a proper. Mirror is a improper. So effectively, it should give us a mirror only, right? Because the handedness has changed. Twofold is not changing the handedness, but twofold followed by the mx is changing the handedness. So let's take a page and what we want to do is we want to do twofold followed by the mx. Yeah. So now we need to talk about how twofold and m plus is going to change the things. Okay. So let's take a page one. Page. We'll see on the new one. 1, 2, 3, 4. Let's talk about the twofold followed by m plus. So this is our twofold, and this is the m plus. Just to be completeness, this is m minus. Okay. So starting with the point 1, let's apply the twofold. So twofold will turn 1 to the 3. 1 will transform to the 3. But we need to put some dash over it because, yeah, no need to dash, no need to put dash. 1, 2, 3. But now what is happening that the mirror, there is along the mirror which is m plus. So 3 will transform to the 1. But there is a problem over here. It was the proper, and this is the improper. So this one and this one, they are different from each other. There is a change in handedness. So the one has changed to the one dash. The handedness has changed, which can directly be accomplished instead of going to the twofold and m plus. If I just apply the m minus, so the handedness of one will change. So this entire thing will be accomplished by the m minus. And we can write our answer over here that it will transform to the m. Doing like this, following the same procedure, one can find the entire thing, like how the one can complete this particular table. And let me write the answers for all of them, like how it is going to be, how what answer will going to be like. So it will be the mx, it will be the m plus, it will be the 4, 4 inverse, 2, 1, m plus, my, m minus, mx, and it will be the 4 inverse will be the followed by the 1 will be 4 inverse itself, and this will be the 4, and this is 1, 2, m minus mx plus my. It will be the mx, my, m minus m plus 1, 4 inverse 2, 4, m plus m minus m x, my, 4, 1, 4 inverse 2, my, mx plus m minus 2, 4, 1, 4 inverse mx, sorry, m minus m plus my mx 4 inverse 2 4 1. So we can see that all of them, they all are forming the closure, because one followed by the two is giving me the elements which is itself, which was already there. Okay, and also for all of them the identity is there, like not going to affect by anything. Something like multiply one thing with another and it's not going to affect, that is m, that is 1. So that 1 is 1, for 2 it's 2, like nothing is going, nothing in, things are not changing, the operations are not changing, mx is remaining as n it is. So we have the identity. So the thing which we were looking for, the this four things, the closure has been confirmed because all of them are giving the, when we are apply the operation followed by, all of them are giving the element which is closed within the particular set, this particular set. Associative, we know that uh, 2 followed by 2 and followed by 4 is same as 4 followed by the 2. So in the symmetry, in the case of crystallography, we can say the associative is most of is followed. Identity, yeah, there is a identity is there for all of them. Like identity means nothing is going to change. That is, one is already available to us and it's not going to change anything. So we can see this particular entire column. This one, it's not changing anything. And the last one is the inverse. Like for everything, is there inverse is available to us. And yeah, for all of them, we can see that is the inverse is available and it is along this particular diagonal. And that's all. We have solved, we have, it satisfy all the four properties, all these four things for this particular, the set of the symmetry operations, and we have solved this particular question number 6.